Title of this lesson, 4.6, Modeling with Exponential and Log Functions. So we're not done with these yet. This is our final lesson, by the way, with logs. If you go further with math, you find that logs pop up in some interesting places. Even in statistics. Okay, statistics, there's some log stuff that pop up in there as well. So if you do, hey, at least you got a good background knowledge of it. Our objectives: solve literal equations for a specific variable, create models for exponential growth and decay, and then apply logistic growth. Okay, so just those three things we're going to be focusing on. So let's go ahead and jump into it. Okay. So here's what we're going to do. So we will use the skill of solving equations for a specific variable, which we've done in the past. But now we're going to do it for the exponential and log equations. Okay, so those literal equations that you talked about, like in Algebra 1, Algebra 2, and even in here, at the very beginning, we talked about how do you solve for a specific variable when you have an expression with a ton of variables. We're going to do the same thing for logs now, okay, and exponential functions. Given that p is equal to 310 e to the 0.00965 t, we're going to solve for t. Okay. Now, some problems, you only really have one direction to solve it. Like there's only like one pathway you want to use. For other problems, you might have multiple pathways to get to your answer, okay? Which can be confusing if you're working with someone, so you don't want to feel like you're incorrect. For this problem, the first thing you want to do is you want to isolate your exponential part. That's this guy, okay? So I'm going to get that by itself first before I do anything else, because that has the t in it, right? So to isolate it, it's multiplying by 310, so I'm going to divide by 310. So p over 310 equals e to that power. Now that it's isolated, I can go ahead and start, using log to both sides. Now for this one, I'm going to use the natural log because that's going to help me get rid of the base here. Yes?
Why did the exponent become negative?
What negative? There's no negative. Thank you. But yeah, natural log p over 310 equals natural log e. I did it again. Wow. I think, you know what? There are some exponential ones where there's negatives in there. My brain's just probably thinking about that. Who knows? So taking the natural log to both sides, that's going to allow me to get rid of this e, because this is just going to be the exponent here. So on this side, we keep the natural log. Over here, it just becomes 0.00965 t. Okay? And then my last step, if we're multiplying by that decimal value, we're going to divide by that decimal value. Now over here, it kind of looks messy at first. So you have the natural log, and then the argument's p over 310 divided by 0.00965. So that's what t is going to be equal to. Okay? You don't need to do this, but sometimes it helps to break apart things if you're able to. So I'm going to put or here. So another equivalent equation. We know with division you can do the same thing as subtraction. So if you really wanted to, you could write it like this, using that property. Okay. The only reason why I would think that you would want to write it like this is maybe it's easier to type in the calculator. I don't think so, but again, I just want to show you the option that if you did break that apart further, you could. But in this case, it doesn't really simplify it any more than what it is. Okay, so any questions? Solve for a specific variable. Again, start off by getting the exponential part by itself. Okay, now let's talk about exponential growth and decay models. Let y be a variable changing exponentially with respect to t, and let y not represent the initial value of y when t equals 0. Okay. Then, for constant k, all right, now I'm going to have two situations. I don't know how you want to divvy up your notes. I'm just going to draw a line here. Okay, on the left-hand side, I'm going to talk about characteristics of what a logistic, well, not logistic yet. I'm jumping ahead. What an exponential growth is. And on the right-hand side, I'll explain what, a decay graph looks like, an exponential decay. Okay, so here we go. On this side, if k is positive, then y equals y naught e to the kt is a model for exponential growth. Okay, so let me just, let's use some colors here. So here it is. So this is what your exponential growth model looks like. Okay, and if the constant k, by the way, that constant, it's very specific to the population. Okay, so all population growth models follow this trend, but for the specific population, it might change or vary by some specific amount. So that k term is what it's doing there, okay? And again, that's going to be different for each population, okay? So let's take a look at an example of something that has that exponential growth. So let's go back to that interest problem that we've been talking about the past couple times here. So we use that model to indicate continuous growth, right? It was continuously compounding, okay? And graphically, it looks something like this. Okay, so there's our exponential growth. And let me just I'll put next to it like an example of it. So you can say y is equal to like 2000 e to the 0.06t. Okay, so there's an example of what exponential growth would look like for us. The k term, in this case, would be our r value, which is interest rate. So k could be anything when it comes to growth models here. In this case, it was interest rate for that one. So just a little small example underneath it. Okay, if k value is just less than 0, then our model's going to look like this. Okay, and it's a model for exponential decay. And let me just underline that. So if you look, it's the same model. The only difference is k is going to be negative in this case. All right, which will change the whole thing because we have a negative exponent. It's taking the reciprocal of the value, so you're going to have a fractional looking fraction here, or function I meant to say. So an example of something like this, and we're going to see this later on in the lesson, okay? This is used for modeling population growth, okay? So if that k value is negative, you're going to see something like this. Okay. And here, let me just tell you what these values are. So p naught, or p sub 0, is your initial population of anything. I don't know, rabbits, foxes. We'll do biology, bacteria. Okay. P of t, okay, represents population as a function of time. I don't know, did Barber do anything in biology with population stuff with bacteria?
Oh, yeah.
Yeah. So I could have collaborated on that, I think. All right. So any questions on those definitions there? So again, the models are the same. It's just what you use for variables depends on the context of the situation here. So let's put some context to it. All right. So the first one we're going to try out is going to be with investments. Okay. So here's our first example with it. Suppose that you have $12,000 and is invested, and at the end of 5 years, the value of the account is $14,952.92. Use the model, A equals PERT, to determine the average rate of return, we'll call R, under continuous compounding. Okay. Now, reading about this problem, that means we're in this round here. Okay, we're over here in the growth. Obviously, because you went from 12,000 to 14,000, close to $15,000. So yeah, you're seeing some growth here. And we're going to use this formula to figure it out. Okay. So if we're trying to solve for R, that's my variable, but everything else is going to have a value. So my account balance at the end of 5 years, that's going to be A for us. Okay. Yeah, let's use a different color. So this will be 14,952.92. P is my principal, what you started with, so 12,000. E raised to the, I don't know what R is yet, I'm going to solve it, but the year was 5, so I'll put 5R up here. So our goal is to solve for R. So the initial setup, not too bad. If I go back to that very first example over there, I told you that you want to isolate the exponential part, right? Before you start introducing log stuff. Okay, so over here I'm going to do the same thing. Okay, so notice that the 12,000 is being multiplied, so I'll divide both sides by 12,000. Now here's just, I don't know, kind of a good thing to think about. If you divide and it comes out to be a nice number, which sometimes happens, then rewrite it as that number, okay? Dividing these two didn't come out to be too nice. So I left that as a fraction, because if I start rounding numbers partway through this, my accuracy of the answer is going to be further and further away from the real thing. So again, if this did come out to be nice, like let's say it was 1.25, great, rewrite as 1.25, but it just doesn't in this case. So this would be e to the 5r. Now again, we have to be careful with how we choose. Could you choose like log base 10 to both sides? Yeah, but it doesn't make sense because that's not going to get rid of the e part. So for here, I'm going to use natural log again because that helps me simplify the right-hand side, okay? So unlike the last lesson where I said you kind of have, you know, if you want to do log base 10, you can, but in this case, it makes more sense to do natural log. So here we go. Take a natural log to both sides. And you could start skipping steps. I'm just showing all my steps here, but I mean, you could just let that be 5r instead of rewriting it that way, but. So let me go ahead and rewrite this as 5r. Okay. And then, well, to solve for r, just going to divide by 5. So as you can see, a lot of these, at least the count balance ones, I mean, you can see how no matter what we're looking at here, they're going to have the same procedure for solving it. So up here, we'll have natural log, and my argument, okay, divide the whole thing by 5. And that's going to be my interest rate. So then the calculate, if you type it in there, you're going to get 0.044. So therefore, he was looking at a 4.4% rate of return, which not too bad. Okay. All right. Any questions on that? Sound good? I know when people see word problems, they freeze up, but if you know what the formula is ahead of time, which is really half the battle, and knowing what values to plug into it, solving is pretty routine. Okay. Let's talk about bacteria since I just mentioned it. suppose at the start of an experiment in a biology lab, you have 1,200 bacteria that are present in a colony. 2 hours later, the size of the population, I'm going to abbreviate for that, is found to be 1,440. Okay, and just for right now, we're going to assume the growth is exponential. Okay, just so we can use some of our properties. So right now, we're going to assume that that growth is exponential. Okay, a couple things. Part A. Determine the growth constant, K, for this population. So depending on what bacteria you're observing here, they're going to have different growth constants, okay? It's just how we do in nature. I mean, think about it. Population. Is the population that's growing in California going to be the same growth rate as Ohio? No. We have different environments, we have different weather, we have different just, rules altogether when it comes to just certain things. So yeah, it's not going to be the same. So same thing for bacteria. They're going to have different growth constants. Okay. So what I'm going to do is I'm going to use, we know what the formula looks like. It's something like that, okay? And what I'm going to do is rewrite it with some of these variables pertaining to it. So P of T equals P naught e to the K T, okay? So let me just identify what these variables mean. And I kind of did it with the decay model over there with population. It's the same thing, okay? But in your notes, let's just make sure they're all together. So P of T is the population at time T, and P naught is the initial population. Now this we could see is going to be a growth because we went from 1,200 to 1,440. Even if this is a decay, you're still going to use the same formula, okay? So that's not going to change. Let's plug some numbers in. So let's see, down here we're going to have 1,440 because that's what we ended with. P naught, my initial population is 1,200. E, I don't know what the constant is, but I know this happened just 2 hours later. So it's just going to be 2K. Alrighty. Now, just like, well, good news is, even though I erased this example, it's still kind of like this over here. Get the exponential by itself. Okay? So let's divide by 1,200. So we get 1,440 divided by 1,200 equals e to the 2K. So I'll tell you what, in this, I'm going to skip just one little step. Instead of me rewriting the LNs and then simplifying the right-hand side, I'm going to do that all at once. So I'm going to take the natural log to both sides. So if I take the natural log here, I know I'm just going to get 2K. So again, I'm just going to try and skip that step. All right. Last part is just divide by 2, huh? So we get the natural log, 1,440 over 1,200, divide by 2 is my growth constant for this particular set of bacteria. And if you type it in the calculator, you're going to get 0.091. So that is the growth factor for this particular experiment. Okay. So far, so good. But wait, there's more. There's a part B. I mean, if you have to put part A, you probably could guess it's a part B. Could be a part C, but that's a cliffhanger. I can't tell you that right now. That's spoiling the surprise. Okay. B. How many bacteria were there 1.5 hours after the experiment began. And I'm going to say round to a multiple of 5. And that'll make more sense when we get to an answer. But right now I'm not focused on what that means. I'm just focused on how do we even start this. Okay, so the good news is I got the growth constant. Okay, so what I can do, let me just go ahead and circle this. I don't know shapes, that's not a circle, I'm sorry, that's a rectangle. But anyway, let's go ahead and plug values in. Now I know what K is, okay, I know what T is. So let's just put it all together. So let's see. So P of 1.5. So we get the 1200, what we started with. 0.091 is the growth factor, and we're looking at 1.5 hours. We went through all that hard work of finding the growth constant, why don't we use it? Now, the only reason why, I want to be very clear on something, I'm not going to give you something that's tricky, but because we're assuming the growth is exponential, I could do this. If it wasn't exponential and it grew at different rates, then none of this is going to work, okay? So there's little no reason why you can find a growth factor. Okay, so we're going to get, type this in your calculator, we get roughly 1,375.5. Okay, so they want you to round to a multiple of 5, so instead of making that 1376, I'm going to keep it as 1375. So for some reason, this biology lab just wants to keep it in multiples of 5. There has to be some reason for it.
Figs.
Could be that, yeah.
Probably.
Okay.
They're well, wait. Well, sig figs is a chemistry thing, but they might have still been applied.
No clue. No idea. Now, there's a part C. When will the population size
Way out. Never mind.
reach 4,800? Okay, no clue why they want to know this, but they just want to figure out, maybe that's the magic number for them. Maybe when they hit that, it's like, okay, something bad happened. Maybe we got to warn the public about something, who knows. Okay, so our initial, let me rewrite this down. So our initial equation looks like this, okay? And again, I know the growth factor and stuff. I just got to solve for t, because that's the one part. Okay, so 4,800 would go into this spot. Okay, what we started with still stays the same, so it's 1,200. E to the 0.091 t. I'm just going to solve that for variable t, which is the very first thing I did in this lesson, right? And kind of continue with it. So let's divide. We'll divide by 1,200. Now here's a case that when I divide by it, I do get a nice number, so I don't have to leave it as a fraction. Okay, if it does come out to be like a good integer response or answer, then leave it like that. So there, 4. We'll take the natural log to both sides. Again, I'm not going to show that step where I'm taking the natural log to here. We know what it's going to look like. So the natural log of 4 equals 0.091t. Okay. And we'll divide. Finish. And the time, okay, is roughly 15.207, so we can see all the values there. I would recommend, I mean, you guys will have practice with this anyway, but anytime in your in a math notebook and you have your professor putting numbers and stuff on the board, and I wish we had time to where I could have you guys take a moment and type it in, but at least on your own time, try to go back through the notes and type those in, make sure you get the same numbers, okay? Because you can have all the work correct, but if you're typing it in wrong, well, not gonna get the right answer, are you? Okay, any questions so far? Okay, now here's what we can do. Do you see how base E is very simple to work with when it comes to those models, right? It's pretty good. So what if we have an exponential that isn't in base E? Well, here's what we can do instead. We can take that exponential and convert it to base E. That way it's easier to work with, okay? So let's do that next. So let me show you how that's done. exponential expression using base e. Let t and b be real numbers, where b is greater than 0 and b can't be 1. Then b to the t power is equivalent to e to the natural log b times t. Okay? So these two guys, I'll put this in red. Okay, so these two are the same. Now, why is it the case? Let's take a look at that. All right? I don't want to just give that to you without actually showing you. So let me put it underneath here. We can show this by using the power property of logs. Okay? Let's take a look at that in action. So let's start with e natural log of b multiplied by t here. Okay? So we're going to work backwards a little bit. So I'm going to start with this and see if I can't lead us to b to the t power. Okay? Now, a little bit of manipulation with the exponent. I could rewrite this like e to the natural log of b, okay, raised to the t power. Okay, that's equivalent, because if you think about it, power to power, you multiply it, so I get the original. So I didn't change nothing, I just kind of rearranged it. Okay. Now, think about our rules of logs. Because this, okay, has the same base here, right, e and e, then this whole thing simplifies to just the argument, which is b, and then we still have the t power there. So there we go. So these are equivalent to each other. So let's use it. Okay? So let's go back to like one of these examples and see if we can't rewrite it using a base e instead. So let me try this example over here. Okay, so part A, given p of t equals 1,000, 3 to the t over 2 power. Write the rule for this function using base e. Okay? So I'm going to rewrite this to an equivalent form just with e as a base. Now, is there anything wrong with this? Can you use this? Yes. Okay. I don't want you to think like, you know, this is something we can't solve with as is. Like if I had to solve for t, you can. In fact, looking at it, just briefly, I would say you would probably use a log base 3, which, I mean, the calculator can handle it. But let's just try and see if we can't convert this. Okay? So right down here, so p of t equals 1,000, and then 3 raised to t over 2 power. Now, let's do a little side work here, okay? Let's mess with the exponential part. So let me just circle that. I'm going to mess with just this. Because my goal is to change this to some e, some base e with some power, okay? So we know this, that 3, the t over 2, okay? And that's me using this formula over here, okay? Is equivalent to me rewriting it as e to the natural log of 3 t. And then we're going to raise, well not raise, but multiply this by a half, I should say. Okay? So can I put this whiteboard over here? Let's do side by side here. Just for right now. Let's just side by side comparison. Okay? So looking at this right here, all right, so whatever the base is going to be the natural log with that as an argument, okay? And then whatever the exponent is, which in this case it was t, in our case it was what, t over 2? So that's going to be right here, okay? I just split t and a half, that's all. If I multiply t and a half together, I get t over 2. So that's what I did. Now, why did I split the t in the half part? Well, let me show you. Okay, so now we can continue to rewrite this using some properties of logs here. This is the same thing as e to the ln of 3 over 2, okay? And t next to it. So now I'm going to bring the half in. And then you can type that in the calculator to get e to the 0.5493 t. Oh, there's a 1 there, 1 t. It's a big decimal. Okay. That's probably the toughest part of this problem is to take what the exponential was originally, use that equivalence property, and just breaking it down simplified. Okay? So now that this part's done, we can rewrite it. So this is p of t. Okay? So approximately, because again, we're kind of rounding here with the decimal, so it'd be 1,000 e to the 0.54931 t. Okay? So this equation and this equation will pretty much give me the exact same results, except that one has a base c in it. So for part B, let's go ahead and actually convince us of it. So let's find the function value for t equals 4 for both functions. In part A. So what I'm going to do, guys, is I'm going to plug 4 into both of these and see if they come out to be the same answer. Okay? If I did this correctly, they should come out to be the same answer. So let's see. P of 4, I'm going to plug into the first one. So 1,000, 3 to the 4 over 2 power. Okay. And when you type in the calculator, you get exactly 9,000. Now let's plug it into that new function I created, and hopefully we get close to the 9,000 mark. So P of 4 equals 1,000 e to the 0.54931 times 4. Okay, so there we go. And type in the calculator, which I wish we had a little bit of extra time because I'd love for you guys to type it in and see it. But we do get approximately 9,000. Okay, it comes out to like 9,000.0000000, and it's like a couple values at the very end. So it's, like I said, approximate or very close to the 9,000 mark. So it works. Okay, that's awesome. A lot of times in mathematics, we like to find ways to change functions to where it still models the same behavior, but maybe easier to work with. Okay? Alrighty. Let's now keep moving on here. Okay, but any questions up to this point? If we're okay? Again, this will take a little bit of practice to just know how to work with that. Okay? Alright. Can I erase with this? Let's see. Oh, that's not too bad. Nice. Yeah, take it back. Maybe the red doesn't like to erase that. Yep, red is being a troublemaker. Okay. All right. So let's create now. Create a model for exponential decay. We've been talking a lot about growth. Let's talk about decay for a little bit. Hospitals utilize the radioactive substance iodine-131. 131 in the diagnosis of the thyroid gland. The half-life of iodine 131 is 8 days. Okay, so meaning like after 8 days you get half the substance that you had originally. Okay, however many don't know what the volume or what the mass would be for that, but however many that you have of iodine 131, depending on what the situation is, you get half of that after 8 days. Okay. The following function represents this situation. Q of t, Q naught, e to the kt, where Q of t is the amount of iodine 131 remaining after t days. Okay? Now, if you look at the formula I just wrote down, that's similar to all the formulas we've been using, right? The only thing different is, well, the variables and what they represent for that specific problem. It's following the same format, which is nice. Okay. So for part A, we want to determine the decay constant. Okay, so what would be the decay constant for this? They don't give us a lot of information, but that's actually to our advantage, believe it or not. Okay? So let me think about what I'm plugging in here. Do they give me any initial amount? No. I know E's involved. I gotta solve for K, and T's gonna be 8, right? Okay, so we know that stuff. Now, how do I mess with Q naught, right? Because that's something I don't have a number for. Well, we could do something like this. I know that what I'm left with, the end result, is going to be half of what I started with. That's just what half-life means, okay? So what I can do is substitute this into my formula.
Please pardon the interruption.
Nope.
Safe Club meeting is right now in room 202 if you are allowed to come. Thank you.
Okay. So anyway, let me go ahead and substitute that in. What's T? 8. So it'll be 8. Okay. So again, I'm taking Q of T out and putting half of Q naught in there, because half-life is going to be half of what you had originally, equals this guy over here. So notice it didn't really matter. You can see that those amounts are going to cancel, right? It didn't really matter what we started with. So little information was okay for us. That was perfect. So those cancel out. I just get a half of e to the 8k, and then we just go back to our usual routine now. So I take the natural log to both sides. Again, I'm not going to show that step on the right-hand side because we know we're just going to get 8k. So ln of a half equals 8k, and then we'll divide. So our growth constant will be negative 0.08664, which makes sense because, again, if it's a half-life problem, you should be decreasing. So my growth constant should be a negative value for that. Okay. This one had a part B. Let's do a part B. How long will it be until only 0.01 grams remain if the hospital acquires 2 grams of iodine 131? Okay. See, this is something you can do while waiting in the waiting room. Crunch the numbers. I don't know. If I'm waiting for way too long for a doctor, my mind starts wandering, and yeah, I do think about math, but I'm a nerd, so that's just how it is for me. Okay, so we have some information here. I got a growth constant, which is going to help me. Let's plug some values in. So I know that this is what I want to end with. So that's what's going to be equal to. So let me go ahead and write that down. So 0.01, and I'm just using that formula over there. I'll put it in red. Okay. Equals. Now what did I start with? 2 grams. So I actually have a number for it this time. E to my growth constant, which I just found. Now I can use it. Okay. And I want to know how long it takes. So T, time. I'm trying to figure out the time part. Any questions on how I plug those values in? Now we just solve. So first step, I want to divide by 2. So this would be 0.005 equals E to the negative 0.08664 T. And then we'll take the natural log. Again, I'll just kind of leave that as just the exponent over here. I'll just simplify. Okay, oops. And then we'll divide by the negative 0.08664. So, drum roll, type it in the calculator, we get 61.2 days. Okay, so that's how long it's going to take to go from 2 grams to 0.01 grams. Which makes sense, because think about it, if you're having it every 8 days, so you go from 2 to 1 to half to a quarter to an eighth, you like just keep going on and on like that. So, yeah, it'll take some time before you get to that low amount. Alrighty. The only thing we got left is talk about logistic growth. Okay, so we're going to see what that looks like. Questions? All right, you guys are awesome. Appreciate you hanging in there. Logistic growth model. Now, unfortunately, you need a little calculus to derive the formula. So I got to just write the formula down for you. Won't be able to derive it. But, you know, come back when you take some calc and we'll look at it together. If you remember that from now. Okay. So here we go. Logistic growth model. Now, here's the deal. I'm going to show you what this graph looks like. We know what an exponential graph looks like. Okay, that's just where it just curves. I'll put it over here. Looks something like this. Okay, a logistic growth model doesn't have that same behavior. Okay, so graphically, let me show you what this looks like first. Okay, so here's my XY axis, horizontal asymptote, and it goes something like this. Okay, now why does it do that? Well, think about it. Think about Ohio for an instance. Do we have a limit of how many people can live in Ohio? Mm-hmm. Yeah, right? Okay, there's only so many people that can live here. That's that horizontal asymptote's telling you. Okay, there is a max limit that could be in terms of people living in this state. Okay, that's what the asymptote is telling me. So it can grow, the population can grow, but over time, due to, well, just living conditions and food supply and different things, there is a value that it gets closer to but doesn't quite hit. You know, it's like your maximum there. So that's different than this guy, right? Because this is telling you it just keeps growing on forever, which we know in the real world doesn't work with all situations. So we have this model to help us with it. So right here, we call this a point of inflection. Okay, that's where some of the values start changing even more. This up here is the rate of change, but it's decreasing. Okay, it's not growing as fast anymore because we're reaching that maximum value. But at the very beginning, our rate of change is increasing quite a bit because we have, well, space, you can call it. Okay, you have quite a bit of room at the very beginning of this graph before you hit that asymptote. Okay? So, graphically, are we okay with what logistic growth looks like in comparison to an exponential? So let me go ahead and put some details underneath here now. Okay? So a logistic growth model is a function written in the form of y equals c plus a e to the negative bt. Okay? So that graph that I showed you right there, that's what it's graphing right there. It's that function. Now, what you could also do, and we do this for a good reason, you'll see in a moment. See how that e has a negative exponent? So we know a negative exponent is going to find the reciprocal of it. So I'm going to put down here, or you could rewrite it as, well, I'm not going to squish it. That would be bad. Hold on. I'll put it next to it. So, or you could rewrite this as c over 1 plus a over e to the bt. So just, again, the only difference is me taking the negative of that exponent and flipping it as its reciprocal. Okay? All right. A little historical note. I wanted to include something in with this, okay? So this was named and studied by a 19th century, Belgian mathematician. And sociologist. Pierre, I'm not even going to attempt to say the last name. Don't want to insult the guy. We're going to just stick with Pierre. Okay, I guess, how would you say it?
Verhulst.
Verhulst? Think that's good? Yeah? Okay. I think that's good enough. But yeah, he was the guy who was messing with this and coined and termed it. Okay, so some things underneath here. A, B, and C are positive constants. Okay. Now, let me ask you this. If I wanted to, and you're not going to be graphing these, but if I wanted to know what is that max value, right? How do you find that HA? Okay, it's pretty simple. So I'm going to write a little note on how to find the HA, okay? So let's look at the term A over BT. Okay, so I'm going to look at just this guy right here. So let's look at that term for just a little second here, okay? As t goes to infinity, the term A over B e to the bt, sorry, will approach 0. Okay? Now think about why that's the case. In the denominator of that fraction, it gets bigger and bigger and bigger and bigger, right? What if you had 1 over a million? Is that getting closer to 0? Yeah, okay. So that's why it's saying it's approaching 0, okay? Now, here's the cause of it. So the function y equals c over 1 plus a over e to the bt will approach c over 1, which will be our HA. Now, I don't think I took a big jump with it, but think about something for a moment. If this approaches 0, the denominator would be what? 1 plus 0, right? Which is just 1. So that's why we get c over 1, which is just c. Okay, so that's going to be our HA. Okay? Now again, we're talking about approaching things, okay? So that's the key part there. I'm not saying like that equals 0 automatically. It doesn't. It approaches 0. Therefore, it's not really going to be affecting the whole entire function as t goes to infinity. Okay. So I got one example with this, and that's it. Call it quits. Okay. I'll put it over here. I think I can. Well, we'll see if I can fit it all on this board. So given p of t equals 4, 1 plus 8 e to the negative t, part A, determine the population in 2 years. Okay, so this is my logistic growth model, just for some population, I don't know. I didn't really model off of any population. That takes too much time. I don't have that kind of time right now to create models like this. It would be cool, it would be fun to do. But let's just say that's my model for some population. And what's it gonna grow in 2 years, okay? So let's do that. So p of 2 equals, I'm just gonna plug 2 into here, okay? So it's gonna be 4 over 1 plus 8 e to the negative 2. Okay. Now here's what I'm gonna do, because again, I want you to try and plug this in your own calculator when you have time. Okay. This is gonna be 4 over 1 plus 8 times 0.13534. I'm gonna at least tell you what this number is. And when you type all that in there, you get 1.92. And this is gonna be measured in the millions, okay? So again, when you actually have some time, you can at least see if you get the same value when you plug that in. Okay. Part B. Use the function to predict the time required for the population to double. When t is 2 years. Okay? So that's what we're going to figure out next. So we're going to still use this guy. Let me just outline it in red. So I'm still using this, but now I want to know, when does it double when t is 2? Okay? Well, what was the population when t was 2? 1.92, right? So to double it, that's 3.84. So 3.84 equals 4 over 1 plus 8 e to the negative t. Okay? Now we're going to solve that for t. Now this one has a couple more steps involved, and I would recommend not to do too much in your head. Okay? Try to take it one step at a time. So what I'm going to do first is multiply both sides by 1 plus 8 e to the negative t to both sides. So that's going to reduce this out, okay? And doing that, we get 3.84 times this guy, which I'm not going to multiply through, you'll see why, equals 4. So I'll just draw an arrow to show what direction I went in. So that's what I get here. Now, again, I want to solve for t, so if I'm multiplying by 3.84, let's bring that over to the other side. Okay? So I get 4 over 3.84. Okay? And I don't want to switch that. Hold on. I need some space. So we get 1 plus e to the negative 8t equals 4 over 3.84. Now I'd want to subtract 1 to the other side, because again, I want to get the exponential by itself. So we get e to the negative 8t equals 4 over 3.84 minus 1. Now I'm back to all those problems we talked about at the very beginning of this lesson. I could take the natural log to both sides, right? Okay, I'm out of space, so I'm going to finish it on this board here.
How did it change to e to the negative 8t?
I'll do it again. What am I doing? The 8 should be here. Thank you. Appreciate that. Why is my brain doing that all of a sudden? I don't know. My apologies. Appreciate you catching that though, because that would have been tragic.
Yeah.
Okay. There we go. Yeah, I have no idea why I was doing that. Okay, so now we're gonna what? Divide by 8. Before I take the natural log, since I forgot about the 8. So e to the negative t equals 4 over 3.84 minus 1 over 8. Take the natural log. I'm not going to simplify it there. I'll just make it negative t. Okay. So again, I'm just not using that extra step for simplifying. We have 30 seconds left. Let me just finish that, and that's it. This is going to be the case. Okay. Last step: take the negative to the other side. So t is equal to negative natural log of all this stuff. And here's the deal. Could you simplify what's... Oh, sorry. Change that. Can you simplify what's in the argument here? You could, but you have a calculator that can do that work for you, so you don't have to necessarily do that. So when you solve it, you get 5.26 years. Okay. Alrighty, guys. So, apologies for that little mistake there. Any questions?